Welcome to Naradar Academy. In this video, we are going to discuss about matrix of linear transformation. Okay, suppose we have two vector spaces V and W. They are finite dimensional over a field F. Dimension of V is M, dimension of W is N. Okay, now let us take any two bases for this V and W. So, since this is V is of dimension M, no, so I am going to take V1, V2, etc. Vm is a basis for V and dimension of W equal to N. Therefore, I am taking W1, W2, etc. Wn a basis for W. Okay. And let me take a linear transformation T from V to W. Right. Then I am going to find the image of this basis. Image of this basis with respect to this linear transformation. So they are given by T of V1, T of V2, etc. T of Vm. Already we have discussed about linear transformation from one vector space to another vector space. In that video itself, I have given one statement that a linear transformation is completely specified by basis of the vector space. Okay, if you want to completely identify the linear transformation, it is enough if you study about the linear transformation about its basis vectors. Okay, so here T is completely specified by T of V1, T of V2, etc. T of Vm. So these are the vectors in your W, isn't it? V1, V2 are taken from capital V and their images will be in W. But W is having W1, W2, etc. Wn as a basis. That means these M vectors can be written as linear combination of these W's. Okay, so I am writing T of V1 equal to A11 W1 plus A12 W2 plus etc. A1n Wn. That is T of V1 is written as linear combination of W1, W2 etc. Wn. In that way I am writing all the vectors. Okay, so now I am going to write the matrix. See, write all the coefficients of W1, W2 etc. Wn. So this is a matrix I am getting. No, this matrix is called matrix of the linear transformation with respect to the given basis. Okay, with respect to these two bases, this is the matrix of the linear transformation. Suppose if you change the basis, okay, if any one of the bases is changed, this matrix will get changed. Okay, so the matrix of the linear transformation depends completely on the choice of basis. Okay, we know that, no, that is for a vector space we can write so many different bases. So the matrix also varies according to the choice of our basis. Okay, now let's see some problems. This is the first problem. Find the matrix of the linear transformation T from V3 of R to V3 of R. That is R3 space, isn't it? V3 of R to V3 of R given by T of ABC equal to 3A, A minus B, 2A plus B plus C with respect to the standard basis E1, E2, E3. See, this is V3 of R, no? This is a vector space over the field of real numbers. And this is also the same vector space over the field of real numbers. Here the linear transformation is defined like this. We have to find out what is the matrix of the linear transformation. Okay, so first, now let us write the values of E1, E2, E3. This E1, E2, E3 is called the standard basis. E1 means 1 in the first position, remaining positions are 0. E2 means 1 in the second position and the remaining places are 0. And E3 means 1 in the third position and the remaining places are 0. Okay, so these are E1 and E2, E3. So this will serve as the basis for both domain and range. Okay, so this problem will be very simple because both the domain and the range are same, and with respect to the same basis only we are going to find the matrix. Now let us write the definition of T. What is given? T of ABC equal to 3A, A minus B, 2A plus B plus C. So what is T of E1? T of 100 equal to 3A. 3A means what here? 3. A minus B. So here it will be 1 minus 0, 1. Next one is 2A plus B plus C. So 2 into 1 plus 0 plus 0. So simply 2. So this 3, 1, 2 is the image of E1, isn't it? This belong to the domain and this belong to the range. So for range also the same basis we have. So this I have to write it as a linear combination of E1, E2, E3. Okay, this 3, 1, 2 vector is there, no? This is in the range. This vector I have to represent it as a linear combination of E1, E2, E3. Since it is given as standard basis, you can simply write 3 into 100, that is first coordinate into 100 plus second coordinate 1 into E2 010 plus third coordinate 2 into 001. Okay, so T of E1 equal to what? 3E1 plus 1E2 plus 2E3, right? So we write the image of E1, that is T of E1, as a linear combination of E1, E2, E3. In the same way, you have to do it for E2 and E3. So T of E2 equal to, what is E2? 0, 1, 0. So apply the definition. 3A, it will be 0. A minus B is what? So 0 minus 1 is minus 1. And 2A plus B plus C, it will be what? Simply 1. So this is the image of E2. Next, this image of E2 has to be written as the linear combination of E1, E2, E3. So for that, simply how you have to write? First coordinate into E1 plus second coordinate into E2 plus third coordinate into E3. Okay, so T of E2 is equal to 0 E1 plus minus 1 E2 plus 1 E3. Then for the third vector 0 0 1 T of E3. T of E3 equal to T of 0 0 1 equal to, what's the definition? 3A. So 0. Next one is A minus B, that is also 0. Next one is 2A plus B plus C. So it will be simply 1. So this is image of E3 in the range. So this we have to write it as linear combination of E1, E2, E3. So simply how will you write? First coordinate into E1 plus second coordinate into E2 plus third coordinate into E3. That's all. Now we can write the matrix of the linear transformation. So how will you write? For all the three vectors, E1 has to come in the first row, E2 in the second row, E3 in the third row. Okay, write coefficient of E1, E2, E3 in the first row. So 3, 1, 2. Okay, here 0, minus 1, 1. 0, 0, 1. Okay, so this is the matrix of the given linear transformation. See, for writing this matrix, no need to write here and all. This and all, no need to write. Directly, once you find the image, T of E1 image you are finding here, no. So this will be your first row. And here T of E2 you are finding, no. That will be the, what is this? 0, minus 1, 1. That will be the second row. And T of E3 equal to 0, 0, 1. That will be the third row. But this you can follow only when you are having E1, E2, E3 as the standard basis. When you have only the standard basis, you can write like this, that is you can skip these steps. Okay, immediately after finding the image you can come to the matrix directly. Okay, you can skip these two steps for each image. Okay, but when you have any other basis in the place of E1, E2, E3, you may get any other basis, no. When you get any other basis, this is not possible. Okay, that is why I have explained in this way, but for this particular problem you can skip these steps. Then second problem, find the matrix of the linear transformation T from V2 of R to V2 of R given by T of AB equal to minus B comma A. So this is the linear transformation. What is our space? V2 of R to V2 of R with respect to the basis 1 to 1 minus 1 for both the domain and the range. So domain and range are same and the bases are also same, but this is not our standard basis. What is our standard basis? 1001 is our standard basis, but this is not our standard basis. Okay, but the procedure is the same. Okay, now let's see how to find the matrix. What is the definition given? T of AB equal to minus B comma A. Let me take the basis elements as U1 and U2. U1 equal to 1, 2, U2 equal to 1 minus 1. So they belong to the domain. Now I am finding their image. T of U1 equal to, what is the definition here? Minus B comma A. So here T of 1 comma 2 is equal to what? Minus 2 comma 1. Okay, so we find out the image, but this is not enough for finding the matrix. What you have to do? Write this vector as a linear combination of this U1, U2. Okay, so I am going to take minus 2 comma 1. This is the vector, no, image. Minus 2 comma 1 is equal to A11 into U1 plus A12 into U2, because I don't know what will be the coefficient. For what coefficients these two will be equal, that I don't know. I have to solve and find. Okay, but in the previous problem it is not like that, because there you had only the standard basis. So simply you write first coordinate into E1 plus second coordinate into E2 plus third coordinate into E3. But here it is not like that. Since they have given a different basis, you cannot simply write like that. So for this image minus 2 comma 1, I have to find these two constants. Okay, that is minus 2 comma 1 has to be written as a linear combination of u1 and u2. So let me take like this: minus 2 comma 1 equal to a11 into 12 plus a12 into 1 minus 1. Now you multiply. So what will you get? A11 plus here, that is I am simplifying and equating the coordinate on left and right side. So on left side it will be minus 2, on right side it will be 1 a11 plus 1 a12, that is a11 plus a12 equal to minus 2. And similarly the second coordinate 2a11 minus a12 equal to what? 1. Now add these two equations. So a12 get cancelled. 3a11 equal to minus 1. So a11 equal to minus 1 by 3. Substitute it here. So a12 will be minus 2 plus 1 by 3 equal to minus 5 by 3. Okay. So I find out the image of the first vector and I write that image as a linear combination of the two vectors u1 and e2. Similarly, you have to proceed for the second vector. What is the second vector? 1 minus 1. So t of u2, the second vector, equal to t of 1 minus 1 equal to, what's the definition? Minus b comma a. So it will be 1 comma 1. Again this 1 comma 1 you have to write it as a linear combination of u1 and u2. So let me take it as a21 into 1 2 plus a22 into 1 minus 1. Now simplify and equate the first and second coordinates on both sides. So a21 plus a22 equal to 1 and 2a21 minus a22 equal to 1. So by adding these two statements, I am getting 3a21 equal to 2. Therefore a21 equal to 2 by 3. So substitute it here. A22 equal to 1 minus 2 by 3 equal to 1 by 3. So what is the matrix of the linear transformation? A11, A12, A21, A22. 2 by 2 matrix, because this transformation maps V2 of R to V2 of R, no. So domain is of dimension 2 and the range is also dimension 2. So the required matrix is also 2 by 2 matrix. Okay. So A11, what are the values we found out here? Minus 1 by 3, minus 5 by 3, and here 2 by 3, 1 by 3. So this is the required matrix. Okay. Then next problem. Let V be the set of all polynomials of degree less than or equal to n in R of x. That is, over the set of real numbers, field of real numbers, we are taking polynomials of degree less than or equal to n. And t from V to V is defined by t of f is equal to df by dx. Find the matrix of the linear transformation with respect to the basis 1x, x square, etc. up to x power n. Already we have seen this vector space in the previous video. So this is a vector space of dimension what? N plus 1. Okay, so this basis is containing n plus 1 elements, no? So it's a n plus 1 dimension vector space. Now what is the definition? T of f is equal to differential operator df by dx. Let me take u1 equal to 1, u2 equal to x, u3 equal to x square, etc. un plus 1 equal to x power n. Now t of u1. What is u1? 1. So differentiation of 1 is 0. So this 0 I have to write it as linear combination of these n plus 1 vectors. So all coefficients are 0. So 0 u1 plus 0 u2 plus etc. 0 un plus 1. Next one, t of u2 equal to d by dx of x. What is differentiation of x? 1. So this 1 I have to write as linear combination of these n plus 1 vectors. So 1 into u1, this is 1, no? So 1 into u1 plus all others are 0 coefficients. And t of u3 equal to d by dx of x square. Differentiation of x square is 2x. So this 2x you have to write it as linear combination of these n plus 1 vectors. So 2 into u2 will alone come. All others are having coefficient 0. So if you proceed like this, for the last vector x power n, what you have? T of un plus 1 equal to d by dx of x power n. It is n x power n minus 1. X power n minus 1 means what? It will be un, right? So for un the coefficient is n, for others the coefficients are 0. So what will be the matrix? I have underlined, no? Each and every line I have underlined. So all those coefficients you write in the form of matrix. The first statement, all the coefficients are 0. The second statement, first coordinate is 1, all the remaining are 0. So 1 0 0. The next one, 0 to 0, all others are 0. So 0 to all others are 0. So what will be obviously in the third step? 0, 0, 3, 0, 0. And finally last row will be 0, 0, 0, etc. In the nth place you will have n and the last one is 0. Okay, right. Then next one. Now, till the previous problem, we have discussed how to find the matrix of the given linear transformation. From here on, we are going to find the linear transformation for which a matrix will be given to you. Okay, this is in the reverse way we are going to do. So a matrix is given to me. I have to find a linear transformation T from V3 of R to V3 of R with respect to the basis. Okay, this is very simple because whenever you have the standard basis, the solution will be very simple. So first row, 1 to 1, no, that will be the image of the first vector. So T of E1 equal to 1 to 1 and T of E2 equal to 0, 1, 1, second row. T of E3 equal to minus 1, 3, 4. Okay, so I have written the images of the three basis vectors. Now let me take any arbitrary vector ABC from V3 of R. Okay, since E1, E2, E3 is the basis, I can write this as AE1 plus BE2 plus CE3. When you write it like this, here ABC will become scalars. See, when you write it like this, it is a vector, but when you write like this, here it will be treated as a scalar. So when you take the operator T on both sides, it will be simply A into T of E1 plus B into T of E2 plus C into T of E3. Now substitute the values of T of E1, E2 and E3 here and simplify. What you get? T of ABC equal to A minus C, 2A plus B plus 3C, A plus B plus 4C. That's all. Then next problem. This is the matrix given. T is a mapping from V2 of R to V2 of R with respect to the standard basis. So T of E1 is the first row, T of E2 is the second row. Let AB belong to V2 of R, then AB can be written as AE1 plus BE2. Here it is vector, here A is a scalar and B is a scalar. So when you take T of AB, it will be A T of E1 plus B T of E2. So simply A into cos theta minus sin theta plus B into sin theta cos theta. So if you simplify, you will get the transformation as A cos theta plus B sin theta, comma minus A sin theta plus B cos theta. That's all. Thank you.